Hi, welcome to Lesson 14e, Differentiation from First Principles. The goal of today's lesson is to learn how to differentiate a function the long and difficult way. We're going to be doing some differentiation of functions as we proceed through this unit, and we've looked at how to find the derivative function or the gradient function of a curve between 2 points by looking at the gradient of a tangent at a specific point on the curve, mainly the point of tangency. And then we're going to be looking at how to find that derivative, which is the noun. And so if we were to look at a curve like this, we've looked at average rates of change, and to find the gradient of a secant through 2 points on a curve, we would be looking at some point that we're interested in. So at x equals x value of a, we've got the y value of f of a, so that's the point P, a, f of a, right there. And then if we take some general point on the curve of this function f of x, we see that this point Q is this general point x f of x. So xy is x f of x. And we can find the average rate of change of the curve between those 2 points, which ends up being the gradient of the secant between those 2 points. And we can calculate that by this formula of f of x minus f of a, which is y2 minus y1, over x minus a, which is x2 minus x1. So the delta y, or the y step, over the delta x, or the x step. And that will find us the gradient of the secant, or the average rate of change between those 2 points. We've done a lot of that average rate of change stuff, and now what we're going to do is we're going to redefine a little bit of this so we can find the instantaneous rate of change. And generally the instantaneous rate of change is the rate of change at one specific point on the curve. Now with our techniques we can't find the rate of change at one specific point yet. But if we take this a f of a once again, and then point Q, instead of having it x f of x, what we're going to do is we're going to say, well, this x value here is some h, some horizontal distance away from a. So the x value is going to be a plus h, and the y value is going to be f of a plus h. So the function f of x evaluated at that x value of a plus h. So the average rate of change between those 2 points, or the rate of change or the gradient of that secant between points P and Q, will then be f of a plus h, so the y value of this point, minus f of a, which is the y value of point P, divided by the x value a plus h minus the x value of point P, which is a. Again, still delta y, or the y step, over delta x, which is the x step. And if we look at the denominator, we can see that a minus a, once we clear those brackets away, will just disappear, so we're left with just the denominator of h. So that'd be f of a plus h minus f of a over h. And that will give us the rate of change of this function between these 2 points. Now, like I said, we're trying to find the rate of change, or the instantaneous rate of change of the curve at one specific point. So the only way we can get at one specific point is if we move this point, this x value here, closer to this point. So this point Q moves down the curve closer to point P, and therefore this x value moves closer and closer to this point A, which means that this h value gets closer and closer to 0 as the distance between them gets smaller and smaller. The distance between them is going to be approaching 0. So what we end up getting is the gradient function, or the gradient of that secant, is then found, well, actually, as it turns out, now that we're finding limits, we're going to use the limit notation because the distance h is approaching 0, which is a limit notation. So this is now the gradient of the tangent, which would then be the instantaneous rate of change of the function, is then f of a plus h minus f of a all over h as h approaches 0. Okay, so we're doing the same sort of thing. It's still y2 minus y1 over x2 minus x1 when those two a values disappear because they cancel out. O all over h, but we're finding all of this when the limit of h is approaching 0. Okay, so it's going to, that ends up being the gradient of the tangent function at that one specific point of a f of a. So if we then say, okay, well, what's the gradient of the tangent at any general point on the curve? Well, it's simply the limit of f of x plus h minus f of x all over h as h approaches 0. So it's the same sort of thing as this other formula up here, but in this case x was a specific value of a that we already knew, whereas this case x is just some general x value on the curve. Which means that we can find, using this formula, we can find the gradient of a tangent to the curve at any point on the curve. We would just have to substitute in a specific value of x when it was convenient for us. Okay, so this now is actually, so that's the gradient of a curve. It's the gradient of the tangent to the curve, which ends up being the gradient of the curve at that specific point of tangency. And so this is then defined as f prime of x, because the function was f of x, and that is the derivative of the function f of x, and so that's all defined as f prime of x is the limit of f of x plus h minus f of x all over h as h approaches 0. Okay, now that's of course if the limit exists. Okay, but that is now the definition. This is the limit definition of the derivative. This is also called finding the derivative of a function from first principles. We have another form. If our function was y equals f of x, we can then say that f prime of x is dy by dx. Okay, dy by dx is the derivative of y with respect to x. And a couple ways we're going to interpret the derivative of the function. It's going to be the slope of the tangent, if I could spell correctly, the slope of the tangent of a function at any point in the curve. And it is also, that's number one, and number two, it is the instantaneous rate of change of the function y equals f of x with respect to x at any given point. So using this, this is called the difference quotient because we're taking the difference and it's a quotient, a division between two values. Okay, so the difference quotient, which is also, of course, finding the derivative from first principles. So we're going to be taking a look at a couple examples tomorrow, and we just will plow right through it. But this is the basic idea, this is the basic function that we're going to be looking at, and we will continue on tomorrow in class. So thanks for watching, and we'll see you in class.